class fam, it's your boy Nickel here. Let's dive into climate science. You should have your weather and climate page done. You should have your diagram completed from the experiment you chose to do, as well as collected your data, completed your own conclusions, created your presentation, and then used other people's presentations to complete the conclusions to the experiment that you did not conduct, but you used their presentation to answer the questions. Now, since you did that, you've also been able to advance past the level up quiz and the next Science Notebook page that we're going to do. We're going to continue to number our pages. As you can see, I've been lacking to do, so we have 26 and 27. This one would be page 28, followed by page 29, 30, and I'm on page 31, and you're probably somewhere close to that. So on this blank page, this is my next blank page, I'm going to now record something that we're going to call our climate phenomenon. Now, phenomenon kind of explains something that is a big concept that we're going to look at how the little things all contribute to this bigger idea. So we'll put a heading on this page and title it Climate Phenomenon. The first thing that we're going to look at that is a phenomenon of climate is wind. Now, wind is a huge component of climate because the wind is basically the movement of the atmosphere, and the climate is the state of the atmosphere at any specific location on Earth over a long period of time. So when we look at what the wind does, it's going to bring moisture to the land from the water. So it brings moisture to land from water. So as the wind blows across water, it picks up those water molecules, they evaporate into the air, and then that wind provides a force that moves the moisture onto the land, which is dry. Now, when we look at this actually happening on planet Earth, let's draw a cross section here of planet Earth, and this here will be the North Pole, and directly below it here will be our South Pole. Now, these poles are actually technically 90 degrees, and then 0 degrees from there, or 90 degrees away from there, is our equator, and that's at 0 degrees. Now, in between, we're going to estimate about right here is going to be our 30-degree north latitude. Here will be our 60-degree north latitude. Down here is going to be 30-degree north latitude, and I'll estimate again 60 degrees south latitude. So this is not the north. Come on, Nickel. This here is the south. Okay. So what we find with our wind is that actually the equator gets the most amount of heat from the sun. And so in this region, air is going to rise up. As it rises, it cools, condenses, and it starts to move. Now it moves across the atmosphere, and it starts losing its energy. It loses its moisture, and it descends here at 30 degrees north. That air then descends, blows across the surface of the Earth, and then goes and rises again once it heats back up at the equator. Now, the air that's actually between 30 and 60 degrees, we'll skip that for just a second, but we can imagine the North Pole is a really cold place. So as that air cools and condenses, it's going to descend down. It's going to sink down closer and closer towards the equator, but it's only going to get to about 60 degrees north, where it will warm up enough that it will then rise up and create one of these cycles over here. So as you can see, our air is rising at 60 degrees north, so it's going to rise for this cell as well. Now this one is going to go the opposite direction. This air is going to fall back down towards the equator, and it's going to descend at 30 degrees. Now this happens at both sides of the equator, so if we go down, we can make these cells, again, cells of air that are here in our atmosphere is what we're drawing, where air rises, it cools, condenses, and then it descends at 30 degrees. Since it's descending at 30, you can see it will descend here. It will rise at 60 and create a cycle in that pattern. The South Pole is really cold as well. So again, the air is going to descend at the South Pole. When it does, then it will go across the land and it will rise at 60 degrees. Now, each of these different types of air cells have specific names. So these cells that are first from the equator to 30 degrees, these are things that we call Hadley cells. And that's what we would name both of the cells of air that are directly from the equator to 30 degrees north or 30 degrees south. The next cell is going to be called a Ferrel cell. And a Ferrel cell just goes from 30 to 60 degrees. And they're called cells because it's a cycle of air. And then these ones here at the poles are called polar cells. All right, so now that we have this diagram of these different air cells that are here on our Earth, and these would be mirrored on the other side of the Earth, let's get some more information written down about what's actually happening as the air rises and as it descends. So let's draw ourselves a little diagram here to show that we have air that's going to be rising up. This is going to be at some areas of our wind cells. This is going to be at 60 degrees where the air is rising, and it's also going to be at the equator. Now, based on what we've learned about weather, we can assume some certain things that happen when our air rises up. So let's record what's going to happen when we have rising air in our atmosphere. So this air that rises up, if it cools and condenses, it's going to have moisture in the air, and that's going to create clouds. So if the air is evaporating and rising from the earth, it's going to pick up moisture. So this is going to be moist air that rises. It's going to have high amounts of precipitation. And if it has high precipitation and a lot of clouds forming, that means that we have a low pressure system. If we remember the cloud in a bottle, when I released the pressure, made low pressure, we had clouds that then formed. And we have lots of vegetation. Now this is because we have a lot of precipitation. We have a lot of water to let plants grow. All right, so here I'm going to draw with this a cloud to show that this has a lot of precipitation. The air is moist, and it brings that moisture. Now when we have air that then, once it cools and loses its moisture, it moves across the earth, and it then is going to descend upon the land. Now when the air descends, it's going to be pretty much the opposite of the rising air. So we'll call this our falling air because it returns back to the surface of the earth. Now it's lost its moisture, so now we have dry air, and we have low precipitation because there's no moisture in the air. And since the air is coming down and pushing on the ground, this creates a high pressure area. If you remember the cloud in the bottle experiment, when I added pressure to the pop bottle, it took the cloud away. So if we don't have clouds, we don't have precipitation, and if we don't have precipitation, then we're going to have a lot less vegetation. Now, if we actually look at the areas of falling air, that's going to be here at 30 degrees south and 30 degrees north, as well as at our polar regions. Now, actually, something that's really interesting about this is that most deserts around the earth can be located at either 30 degrees north or 30 degrees south. The Sahara is at 30 degrees south. The deserts of the United States are at 30 degrees north. Also, the poles, even though they have a lot of snow on them, they're still considered deserts in some respects. So therefore, we can also apply this idea that we have dry air descending here at the poles, and that's going to cause deserts at our polar regions. All right, so we have rising air and falling air, but it doesn't just move so smoothly here on the earth because of an effect that you guys learned about in the YouTube binge assignment that is called the Coriolis Effect. And the Coriolis effect is going to affect our wind, so we're going to keep it on this page with our wind. And the Coriolis effect is a process that causes fluids on our Earth system. Those fluids are things like water and air. Causes fluids like water and air to curve as they travel across or above Earth's surface. Now, as we watched the videos, they gave us some demonstrations to show which direction it would actually go, so we'll just record that here. So if here is my equator, and this is also the eastern side of my Earth. This is the western side of the Earth, the northern pole, and the southern pole. So what we find is that the Earth is going to rotate from west to east. So our rotation is going in this direction. The Earth is going to rotate in this direction. So as it's rotating, if things move from the equator is actually moving faster because this is a sphere. It's kind of like if you've ever been in a circle before and you've held hands with people, or if you have a jump rope and if you're standing in the middle and you pull that jump rope and it's out further than you and you start spinning around, that jump rope will spin around you maybe 3 or 4 feet away faster than the rate at which you're spinning because it's traveling more distance. And that's happening here on the Earth as well. So when air leaves from the equator, as it does at 0 when we have rising air, that air rises and goes from west and it curves to the east. As it leaves the equator in the southern direction, it goes from west to east as well. So we end up finding these patterns occur, and as the air then descends from the north down more south from the equator, since it's spinning slower in the north, it's going to actually have a curve that's also going to face this direction. Now this is why here in Colorado and in other places, our weather is always coming to us from the west and going to the east, at least most of the time, because most times, unless we have some unique storm, our air is going to be moving in this direction. So it's going to come across the middle of Colorado or come down from Canada from the north, and it's still going to be going from west to east regardless which way it's coming from the Coriolis effect. All right, so we have 2 other factors that are going to contribute to our climate phenomenon, and we're going to record those on our next page. So let's turn the page. For me, I'm now on page 32. All right, these other 2 things, we're going to start by looking at mountains, and mountains affect climate a lot like mountains affect weather. All right, so our mountains are going to force wind to rise as it crosses them. And we have a diagram that's a lot like this, and we'll repeat that diagram in a simplified form. But what ends up happening when wind is forced to rise as it crosses them, it's going to create an area of a wet climate, and then there's going to be a rain shadow that causes a dry climate. Mountains force wind to rise as it crosses them, creates a wet climate and a rain-shadowed dry climate. So if we were to draw ourselves a mountain range here, it's really simple, and the wind direction is going to be in this direction. And we'll say that then where the wind comes from, this is the upwind side of the mountains. This side down here where the wind is coming from and going to, this is our downwind. Now, since the wind is forced up, there's less pressure as you go higher up, and the wind has some moisture in it, so we're going to end up getting cloud development. And this is where our rain then will happen because we have that air is forced into lower pressure, and it's going to actually get all the moisture, or most of it, out of the mountain, or out of the wind in the air, so that when it comes down and that air continues over the top of the mountain, as it then descends, it goes into an area of higher pressure, so we're going to actually have better weather because we have higher pressure and we also don't have as much moisture in the wind, so therefore the downwind side is usually sunny. Now this is why in the Front Range we typically have more sunny days than they do up in the mountains where they actually have a lot more precipitation occurring. Another important thing that we discussed in class that we'll also record here is if we look at a mountain, the temperature will actually decrease. Temperature decreases by 3 degrees Fahrenheit per 1,000 feet increase. So let's say we have a mountain that we start at 5,000 feet. Let's go up to 6,000, 7,000, 8,000, 9,000. We'll say this is a 10,000 foot mountain, a tenner, kind of like a 14er, but we only go 10,000 feet. All right, so let's add units. We're gonna count this in feet. And this is important that we're adding feet here because in our description we said it decreases 3 degrees Fahrenheit per 1,000 feet. So let's say that it is a nice 60 degree Fahrenheit day at 5,000 feet. Then we can predict it would be about 57 degrees Fahrenheit at the same time at 6,000, 54 degrees at 7,000, 51 degrees Fahrenheit at 8,000, 49 degrees Fahrenheit at 9,000, 46 degrees Fahrenheit at 10,000. So we see that the temperature decreases as we increase in elevation. Now, also as we increase in elevation, the air pressure will decrease as we go higher. So we'll just add that as a note here. Also, air pressure decreases as you increase elevation, or we could also call that altitude. So I'll put a little star there because we can't really show that because we don't have a specific number of how much it decreases, so we're not going to include a number there, but we can just say the air pressure is going to decrease because there's less air up there, so there's less air to push on you to provide pressure. All right, the last factor that contributes to climate phenomenon is our oceans. And as you've been learning so far in our climate science unit, oceans are going to do a couple things. First, they're going to provide moisture to fuel our rainstorms. And also they provide a buffer to coastal regions. And actually, they provide a temperature buffer, so I'm going to add temp there, because they provide a temperature buffer to coastal regions. And what I mean by that is that if you have an area of cold water and you have some land that's right next to it on the coast, coastal land, this land is going to be a cooler climate because it's next to cool water, and that cool water will actually steal some of the heat from the land, and that coldness will then be transferred to the land. And if we have an area that's opposite of that, and we have warm ocean water because of the ocean thermohaline circulation, we have coastal land next to the warm water, then we end up having a warmer climate. And when we say that the water provides a buffer, basically what that means is the land is not going to change temperature very much because this water next to it doesn't really change temperature a ton. So therefore it's going to moderate how much the land swings its temperatures. All right, that summarizes our climate phenomenon pages. You're good to go and to move on. Thanks for watching, y'all. Peace.